Exploring Life Chapter 4, Water Part 1. Water is the element that transformed Earth into a living planet, and this is the next step in our journey. But before we explore its remarkable structure and properties, the very features that made life possible, we need to step back and consider the origin of our planet. The universe had already seen eons of change before the birth of our solar system. The oldest galaxies are about 13 billion years old. In comparison, our Sun is relatively young, forming around 4.6 billion years ago. Earth followed not long after, about 4.5 billion years ago. According to the giant impact hypothesis, Earth's early history included a massive collision with a celestial body called Theia. Out of that cataclysm came not only the Earth as we know it, but also our constant companion, the Moon. The Moon has always been more than a beautiful night light. It stabilizes Earth's orbit, drives the ocean tides, and helps maintain a climate steady enough for life to take root and evolve. The video you're about to see is a NASA simulation of this dramatic beginning, the birth of Earth and its moon. From there, we'll return to the central character in this story, water. The simulation, which begins with a collision between a Mars-sized body and our planet, visually illustrates the giant impact hypothesis. The impact was so intense that it vaporized and melted parts of both bodies, ejecting a massive cloud of debris into Earth's orbit. Within hours, this debris began to clump together under the force of gravity, eventually forming two bodies. The smaller of the two became the Moon. The gravity of the larger body, Earth, propelled the forming Moon forward and launched it into a wide and stable orbit, completing the process of moon formation. That was colorful, but pretty terrifying, right? Not surprisingly, early Earth was an incredibly hostile place. Its surface was intensely hot, but over time, it began to cool. Frequent collisions with asteroids likely delivered water, and eventually, Earth's surface stabilized enough for oceans to form. These oceans became the cradle for the development of life. The importance of water for life as we know it is so well established that it has become a central focus in the search for life beyond Earth. Scientists developed the concept of circumstellar habitable zones, regions around stars where conditions might allow liquid water to exist. These habitable zones are shaped by several key factors, including a planet's distance from its star, its size and mass, and the amount of radiation it receives. Fortunately for us, Earth is ideally positioned within the Sun's circumstellar habitable zone, but it's not the only planet in our solar system that falls within this range. Look at the illustration. Earth's orbit lies within the inner part of the habitable zone. Mars, by contrast, orbits closer to the outer edge of the zone. While technically within the habitable range, Mars has colder temperatures and a much thinner atmosphere, making it far less suitable for sustaining liquid water and life as we know it. But this won't last forever. As stars age, including our Sun, their luminosity gradually increases. This causes the boundaries of the habitable zone to shift outward over time. In about 1 billion years, Earth is expected to move inside the inner edge of the Sun's habitable zone, becoming too hot to support life. At the same time, Mars may move into the habitable zone, potentially becoming more suitable for life, if conditions like water and atmospheric stability are met. Let's explore the possibility of life beyond Earth. While life might exist in forms that don't rely on water as we know it, all life we currently understand is water-based, so let's start there. Even if we focus exclusively on water-based life and limit ourselves to just one galaxy, our own Milky Way, the numbers are staggering. The Milky Way contains hundreds of billions of stars, many with orbiting planets. A significant portion of those planets may lie within habitable zones, where liquid water could exist. In other words, the sheer scale of our galaxy suggests we're unlikely to be alone, and that life, including intelligent civilizations, may very well exist elsewhere. Yet, despite decades of exploration, we still have no direct evidence of alien life, at least not yet. We may not need to search light years away to find signs of life. Some of Saturn's moons, like Enceladus and Titan, are believed to hold liquid water beneath their icy crusts, one of the key ingredients for life. So maybe it's not a question of if, but when, as long as we keep following the water. What do you think? So, by now, it's clear why we study water in a biology course. It's a big deal. But why exactly? For starters, water is colorless, tasteless, and odorless. On the surface, it may seem simple, even ordinary. Yet this seemingly unremarkable substance forms the very foundation of life on Earth. It not only makes up a large portion of living organisms but also shapes and sustains the environments where life can exist and thrive. Let's recall our previous lecture, where we explored the basics of atomic structure and chemical bonding. Understanding how atoms interact, especially through covalent bonds, helps us make sense of how molecules like water form. This foundation is essential as we dive deeper into the unique properties of water and its critical role in supporting life. Oxygen and hydrogen have different electronegativities, meaning they attract shared electrons with different strengths. In a water molecule, the electrons are pulled more toward the oxygen atom, giving it a partial negative charge. As a result, the hydrogen atoms carry partial positive charges. This makes the covalent bonds polar, and because of this polarity, water molecules are considered dipoles. This figure illustrates the structure of a water molecule, showing two hydrogen atoms covalently bonded to one oxygen atom. Oxygen needs two electrons to complete its valence shell, and each hydrogen atom contributes one electron to form a stable molecule. Because oxygen is more electronegative, it pulls the shared electrons closer to itself, resulting in a partial negative charge. The hydrogen atoms, in turn, carry partial positive charges. These partial charges, indicated by delta minus and delta plus, make the molecule behave like a tiny magnet, or dipole. In its liquid state, water molecules are connected through hydrogen bonds. These bonds form due to the electrostatic attraction between the negatively charged oxygen atom of one water molecule and the positively charged hydrogen atom of another. Imagine a pile of magnets, how they naturally stick to each other. Water molecules behave in a similar way, drawn together by these weak but important hydrogen bonds. Although not as strong as polar covalent or ionic bonds, hydrogen bonds are essential in giving water its unique and life-supporting properties. We've explored water on the largest scales, how it shapes planets, defines habitable zones, and guides the search for life. In Part 2, we'll turn inward, zooming down to the molecular level to uncover how water actually works, its structure, its bonds, and the remarkable properties that make it the foundation of life.